Welcome to the Explainer. Today, we're going to peel back the layers of mathematics. We're not just going to look at numbers and equations, we're going to uncover the elegant, hidden structures, the powerful ideas that really, truly power our world.
So let's kick things off with a pretty big question. What if math isn't really about calculating things at all? What if, at its core, it's actually the art of building entire systems? Creating logical worlds from scratch and understanding the very nature of structure itself. That's the journey we're heading out on today.
And our journey starts with the most fundamental building block there is, the number. But as we're about to see, even this simple concept has some pretty surprising depth to it. We all start out learning about rational numbers. They're the ones that play by the rules. You can write them as a neat, tidy fraction. Their decimals either stop or they fall into a nice, predictable, repeating pattern. But then, there's this other, kind of wilder universe of irrational numbers. Their decimals are like a story that never ends and never repeats. They go on forever, with no pattern. You just can't pin them down as a simple fraction.
It's one thing to just say that a number like the square root of 2 is irrational, but the real beauty of mathematics, the really cool part, is that we don't have to take anybody's word for it. We can actually prove it, using nothing but pure, undeniable logic. Okay, so let's walk through this. It's a classic move called a proof by contradiction, and it's a little like playing detective. We're going to start by assuming the exact opposite of what we want to prove. So for a moment, let's just pretend the square root of 2 is rational. That means we can write it as a fraction, p over q, that's in its simplest form. That's key. It means it's totally reduced, like 3 over 5, not 6 over 10. So our first move as detectives is to get rid of that pesky square root. We just square both sides of the equation. That gives us 2 equals p squared over q squared. A little rearranging, and we get p squared equals 2 times q squared. Now, what does that tell us? Well, it tells us that p squared has to be an even number, right? Because it's 2 times something. And this is where the whole thing comes together. If p squared is an even number, well then p itself has to be an even number. Think about it. You can't multiply an odd number by itself and get an even number. 5 times 5 is 25. But wait a minute. If p is even and we follow the logic down the line, it turns out that q also has to be even. And if they're both even, our fraction wasn't in its simplest form after all. We could have divided both by 2, but we started by assuming it was already simplified. That's the contradiction. Our initial assumption just fell apart. It has to be false. The square root of 2 is irrational. Case closed. Okay, that's all well and good. But what happens when the numbers we have just aren't enough? For centuries, this little equation right here, x squared plus 1 equals 0, was a total roadblock. Any number you can think of, positive or negative, when you square it, you get a positive result. So how in the world can you add 1 to a positive number and get 0? It just seemed impossible.
So what did mathematicians do? Well, what they do best, they invented a new tool. They just defined a new number, they called it I, the imaginary unit, and said its job was to be the square root of -1. All of a sudden, the impossible was possible. And here's the kicker. These imaginary numbers are absolutely essential for things we use every single day, like processing the signals for our Wi-Fi and cell phones.
All right, let's climb to the next rung on our ladder of abstraction. We've talked about individual numbers, real, and, well, imaginary. So what happens when we start grouping them together? We group them using this idea of a set. And it's, one of the simplest but most powerful ideas in all of math. It's really just a collection of things. It could be the set of all the even numbers or the set of vowels in the alphabet. A set is just a way to draw a boundary around an idea.
And once we have sets, we can start doing things with them. As you can see in these Venn diagrams, we can take the union of two sets. That's like grabbing everything from both circles and throwing it all together. Or we can take the intersection, which is only the stuff they have in common, just that little bit where they overlap. It's a really simple visual way to think about how different collections relate to each other.
Okay, so we've got our numbers, we can group them into sets, but now what? To do anything really interesting, we need a super precise language to make statements about them. We need rules for the game. We need logic. And logic is all about being super precise. No wiggle room. Take the and statement. If I tell you it's sunny outside and I'm wearing a hat, that whole statement is only true if both parts are true. If it's cloudy, or if I'm not wearing a hat, then my entire statement is false. As this truth table shows, it's black and white. Okay, now this next one, the if-then statement. This is where it gets a little weird, but stick with me. The best way to think about it is like a promise. Let's say I promise you, if it rains, then I will bring an umbrella. The only way I've broken my promise, the only way my statement is false, is if it actually does rain and I show up without an umbrella. In every other situation, if it doesn't rain or if it doesn't rain and I bring one anyway, my promise is still intact.
All right, we are now ready for the final step on our big ladder of abstraction. We have numbers, we have sets to group them, and we have logic to reason about them. Now we need a structure that can organize huge amounts of information and operations all at once. And for that, we have the matrix.
So what is a matrix? Well, it's just a grid of numbers. That's it. Rows go across, columns go down. Honestly, the best way to think of it, it's basically a spreadsheet for a mathematician. On its own, it might not look like much, but it is an incredibly powerful way to structure and work with data. Now, matrices have their own, let's call it special way of doing things, especially multiplication. It's kind of like this little dance where you pair up the rows of the first matrix with the columns of the second one. It might seem a little strange at first, but this very specific process has a very specific and very powerful purpose. And I know what you're probably thinking right now. Why? Seriously, why on earth would anyone invent such a complicated way to multiply a couple of grids of numbers? What is the point of all this structure? And here's the point. This is the payoff. With matrices, we can take a tangled, messy web of equations that are all connected and represent the entire system as one clean, simple statement. This is exactly how computer graphics programs can take a 3D object on your screen and rotate it or scale it or move it around. They use one matrix to transform thousands of points all at once. It turns total chaos into a single elegant step. That's the power.
Okay, let's just pause for a second and take a step back. Let's look at the journey we've just been on, from a single, lonely number all the way up to these incredibly powerful tools.
You see the pattern here, right? We've been climbing this conceptual ladder. We started with the basic idea of a number. Then we abstracted that into collections of numbers, which we called sets. Then we built a language, logic, to talk about those sets. And finally, we built an even higher structure, the matrix, to organize and operate on everything. And that right there, that's the real story of math. It's not just about crunching numbers. It's about building conceptual tools. Each new level of abstraction lets us tame a new level of complexity, giving us an even more powerful lens to see and understand the world. And all this leaves us with one final big thought. We've seen how these fundamental structures, numbers, sets, logic, matrices, were built over centuries. So if these are the tools we've invented so far, what new structures, what new ideas will we have to invent next to understand the complexities of tomorrow?